Hello everyone, my name is Yiwen Chen. I am a master's student in electrical engineering. I'm about to present my conference paper about the flexible printed potentiometric sensor I have developed for potassium ion sensing. I shall first talk about the background of my research and the potentiometric sensor's working principle, then touch on the design and fabrication of the printed ion-sensitive electrode, and finally discuss the experimental results obtained. The human body is composed of cells. 98% of the potassium element in the body is present in the cells and participates in the biochemical reactions through them. Potassium ion plays multiple critical roles in maintaining the muscle, nervous system, and body's metabolism. Therefore, keeping track of the level of potassium ion can be crucial. In the current stage, most diagnoses about potassium level are based on blood samples. As many important contents in saliva are highly correlated with blood, saliva tends to be employed as a more convenient, cheaper, and non-invasive approach to track the potassium level in human body. The motivation of this research stems from the demand of low-cost and easy-to-fabricate potassium ion sensor that can be used for non-invasive point-of-care testing. For this purpose, we found that potentiometric sensor is one of the simple, highly reproducible, and cost-effective electrochemical sensors. Among different types of potentiometric sensors, ISEs have demonstrated high sensitivity, prominent reliability, remarkable durability, and good miniaturization. Potentiometric sensors are fabricated using conventional microfabricated process such as sputtering, chemical deposition, and lithography. Due to this, microfabricated potentiometric sensors are not cost-effective to be used on disposable basis. In order to lower the processing temperature and cost, inkjet printing technology is used for fabricating the ISE. Inkjet printing is a digital printing process, which means there is no prefabricated mask required, so that the cost is reduced significantly. Moreover, the digital process makes the part modification super easy. As an advanced additive manufacturing technique, inkjet printing is compatible with flexible R2R process with promising resolution and accuracy, which shows great potential in fabrication of printed flexible electronics. The ISE working principle is based on the Nernst equation developed following the microscopic electron neutrality. This type of electrode response and the selectivity are determined by ion exchangers and ionophores. When the analyzed solutions contact the membrane, the interest ions are permeable and caught by the ionophore and cations from the ion exchangers group within the membrane to form complexes, while the interest analyte diffuses from the high concentration to low concentration region along with the ion exchange process, a boundary potential and diffusion potential are developed across the membrane. The membrane becomes positive with respect to the solution side as a potential difference developed over it. At the saturation level, a potential produced by cations already in the membrane prevents further potassium ion diffusion and establishes the equilibrium of the electric force and the diffusion force. Ideally, the EMF between the two electrodes obeys the Nernst equation. If the interfering ions are considered, the model will be more complex, and a constant K reflecting the selectivity should be included. At 25 degrees Celsius, the full Nernstian slope equals to 59.18 millivolts per decade for potassium ion. As the figure shown here, a two-electrode configuration is employed, which consists of a working electrode and a reference electrode. The ion-sensitive process happens on the working electrode, and the reference electrode is employed to complete the circuit and maintain a constant interfacial potential. The voltage measured between the working and reference electrode is directly related to the concentration of the ion of interest in the analyte. Ionophores, ion exchangers, plasticizers, polymeric matrix, and solvents are the basic components in the membrane formulation. In this work, varenomycin was used as the potassium selective ionophore. Potassium tetrakis 4-chlorophenol borate was added as ion exchangers. Common polymeric matrix PVC and the plasticizing solvent mediator bis-2-isohexofabricate were dissolved in THF solvent. To fabricate the ISE, the first step will be printing the metal layer on the Kapton substrate and curing it at 150 degrees Celsius for 45 minutes. The second step is to drop cast the ion-sensitive membrane solution already prepared over the circular detecting area, followed by evaporation for at least 24 hours. Finally, the ISE should be soaked into 1 m sodium chloride solution for at least 12 more hours to establish a steady electrical potential. This figure shows how we set up the ISE for testing. Solutions with varying potassium ion concentration over 10 to the power of -5 to 1 m were made by dissolving potassium chloride powder into deionized water. The detection area where the sensitive membrane covered of the working electrode and some parts of the reference electrode were submerged in the potassium ion solutions, and the EMF generated across them was measured with a high-impedance multimeter. Each data point in this response slope corresponds to the EMF after the sensor reaches to a stable value approximately after 5 minutes. A linear fit over 10 to the power of -5 to 1 m concentration dynamic ranges indicates sensitivity of 50.0 mV per decade of the sensor. Additionally, it can be concluded that the sensor demonstrates an accuracy of 0.19 log of potassium concentration and a resolution of 0.17 log of potassium concentration. Sodium ion, ammonium ion, and calcium ion are 3 common ions with relative high concentration in saliva. For testing the selectivity towards these ions, the mixed solution method was adopted. Mixed solution method is one of the options to demonstrate the selectivity for the ion-sensitive electrode. The plot obtained from this method can clearly exhibit the effective working range of the membrane for complex mixtures, which is more suitable for realistic systems. In this method, the target ion potassium ion concentration was kept fixed at 0.001 m, and the EMF was measured versus fixed primary ion concentration with varying concentrations of interfering ions added from 10 to the power of -4 to 1 m. The EMF generated for varying concentration of sodium, ammonium, and calcium ions are plotted in the figures. Here, the orange line marks the EMF measured without any interfering ions for 0.001 m potassium solution, and the shaded areas corresponds to the concentration range of each interfering ion present in human saliva. The 3 plots demonstrate that the interfering ions don't affect the sensor's measurement significantly over the range present in saliva. The mean absolute deviation in EMF for the interfering ions over the range present in saliva were calculated to be less than 10 mV here. The stability test was conducted by measuring the EMF of the sensor generated in 1 m standard potassium chloride solution for a long time frame. The stability plot demonstrates the EMF generated by this sensor is stable over 12 days. In this work, a flexible printed potassium ion potentiometric sensor with good sensitivity is demonstrated. The ionophore-based ion-selective membrane in the sensor exhibits good performance. The sensor demonstrates a sensitivity of 50.0 mV per decade with an accuracy of 0.19 log of potassium level and a resolution of 0.17 log of potassium level over 10 to the power of -5 to 1 m potassium ion concentration range. The sensor's measurements mostly remain unaffected by the interfering ions present in saliva and show stability over time. This makes the sensor suitable for low-cost point-of-care diagnosis. To avoid fluctuations in measurements with ISE, a three-electrode configuration with an extra counter-electrode should be introduced in order to help the sensing system in the future, as the third electrode will be beneficial to system stability and reproducibility.